Hello ladies and gentlemen, my name is Michael Kuhl. Today we're going to talk about ultracapacitors improving the efficiency of systems in the transportation industry. I have a background in mechanical engineering. I've built a variety of systems, hybrid and fully electric vehicles, from passenger cars to large Class 8 trucks, using advanced batteries, ultracapacitors, fuel cells, engines with advanced fuels, and multiple charging methods. I've also designed multiple energy storage systems, including ultracapacitors and other types of batteries. And I've been working in this industry for over 10 years, and currently I'm the engineering manager at Unique Technical Services. UTS provides engineering services to a variety of clients. We have electrical, mechanical, software, and power electronics expertise. We develop products ranging from handheld electronic devices to full-scale vehicles that roll down the road. We have a strong basis in analysis and testing and have the capability to develop ground-up validation plans. The UTS team has worked with ultracapacitors for over 10 years and has worked in the electric vehicle and energy storage space for over 25. UTS has quite an extensive amount of experience in the transportation industry. Each of the photos shown here on this slide represents a vehicle that UTS has developed in the electric or hybrid electric space. We've worked on trucks and buses, both hybrid and fully electric. We've developed an electric passenger car. We've worked on off-road vehicles, including mining and farming vehicles. We have a grant-funded project on energy recapture on trains, and we've done some service equipment, electric vehicles. And also, as I mentioned, UTS has experience with ultracapacitors. We developed quite a few modules, integrated many modules into vehicles and stationary applications. And the things we've done range from cell packaging, where we've developed modules that have IP ratings of IP67. We did some vibration and shock testing regimes. And we've done cell balancing, passive and active. We've done cell monitoring, so we typically monitor temperature and voltage. If we're doing it simply, we're just doing a stop charge threshold, but sometimes we'll do a full CAN communication method. We've done welded bus bars and bolted bus bars, and a lot of our development focuses around how we deal with the thermal and vibration management, a potting selection or thermal pads, or if thermal is not really an issue, you could do rubber, but something to damp the vibration and something to deal with the thermal dissipation. Here's an example of UTS's experience with actually integrating an ultracapacitor module to improve the efficiency of an electric system on an electric transportation application. This here you're seeing a 24-volt ultracapacitor module paired with a DC-to-DC converter to level the load on that ground support equipment battery. This would cut the peaks and valleys off of the load, which was the defining characteristic of the life of the battery. This particular ultracap module included welded bus bars, passive balancing, a urethane potting for thermal and vibration, and a simple stop charge feedback loop. Another example of UTS's experience with ultracapacitors, here's a bulk storage ultracapacitor module for a hybrid vehicle. This is a 250 volt ultracapacitor module, 2 banks shown here with fan cooling. This particular module set has bolted bus bars, passive balancing, a silicone potting, again a simple stop charge feedback, but also included CAN communication with a number of sensors on the ultracapacitor modules. So today we're going to talk about how ultracapacitors support more efficient transportation applications. So first we want to talk about the transportation industry in general. What tools are in our toolkit? The transportation industry obviously uses engines, but more recently electric motors and batteries. We're going to talk about ultracapacitors. They've been using hydrogen fuel cells, DC fast charging, wireless charging, really anything to achieve some opportunity charging. So to optimize the solution for each application, this can be a difficult problem. How do we use all the tools in our toolkit the right way in the right application and make it most cost effective for our customers? So when do we use ULTRACAPs? When is it appropriate? When will using ULTRACAPs lead to an increase in efficiency for the system in the transportation industry? So let's start with a quick refresher between batteries and ultracapacitors. So starting with capacitors, capacitors have long cycle lives. Some of the manufacturers might state 1,000,000 cycles. This is very different from a battery. Additionally, the capacitors have a low internal resistance. This means that they don't heat up when you pass a lot of current through them. So that means they have high current capability. If they have high current capability, they have high power output. However, they don't store a lot of energy. They can put out a lot of current, a lot of power, but they don't have a lot. And that's why the capacitor here is indicated by a bucket that you can dump out and fill up very quickly. A battery, on the other hand, is more like a large jug with a limited spout. So the battery has a much higher internal resistance compared to the capacitor. And depending on the battery technology, it will range with some value of ESR. But batteries in general have higher energy densities. So you'll have a smaller voltage swing, higher energy, but you'll be limited on the amount of current you can take out because the ESR limits you. But the battery does have a dependency on its current and temperature. So if you push the current higher and higher throughout its life, it will last a shorter and shorter duration. So one thing to note in this area is, how do we talk about that? In the industry, we talk about the amp hour rating of a battery. The amp hours are, let's say, 100 amp hours for a battery. A good way to talk about the current limitation is to talk about the 2C, the C rating. The C rating is directly related to the amp hour. So if I say I have a 100 amp hour battery, the C rate, 1C, would be 100 amps. A good rule of thumb for lithium-ion batteries would be a 2C limit. If you can keep the current below 2C, then you should expect a fairly long life of that battery. If, however, you push the current up above 2C repeatedly, you're going to experience shorter and shorter lifetimes. And that's how we talk about it in the industry. Are you keeping the current below some C rating for that battery size? On the capacitor, we talk about it differently. We talk about the farads, the capacitance of the capacitor. But to calculate the energy content within the capacitor, you can use this equation, half times the capacitance times the voltage squared. But be careful to use the voltage range that it can be actually utilized in the application. And this is typically dictated by your power electronics. So let's compare the size and power then. So we have some ideas of these parameters. So here I show a battery pack that UTS has worked with, and an ultracapacitor module that we've developed. These are just two examples, but they're at the same scale. So the one on the left is the lithium iron phosphate battery pack. It's 580 volts, 105 amp hours, and together this pack that you see, these two boxes, is 60 kilowatt hours. It's roughly 12 cubic feet, weighs about 1,000 pounds, and its C rate, its 2C rating, is about 200 amps. The ultracapacitor on the right, that's a 135 volt peak capacitor bank. It's 67 farads, or 170 watt hours. Notice watt hours, not kilowatt hours. It's 1.5 cubic feet. It's about 50 pounds. But this capacitor bank can output 2,000 amps. So this shows you a bit of a difference between the size, the weight, and the amps that you can put out for a specific capacitor versus battery bank. And how you use these can dramatically affect the optimization of your system. So we think, well, I think I can use an ultracapacitor bank in a particular application we're thinking of. How do I go about it? The first question we should ask is, how much energy do you need? And the next one is how much power do you need? These two pieces of information are going to be critical for sizing and understanding how best to implement ultracapacitors in this system. So, what are your first steps? Typically, you simulate the system. Sometimes this is a back of the napkin calculation just to characterize the system, how much power, how much energy we might utilize. But a word of caution here we'll go through is don't always accept the averages. They don't always tell the story. We're going to go through a couple of examples of things to watch out for. The first one is inertial loads. Those beginning moments of initial spinning up a flywheel or a gear or breaking static friction can be significant on certain applications where those initial starts cause a large current spike to the electric motor you might be using to start that motion. And that's a very good place to look at in detail if an ultracapacitor would be useful. UTS just experienced this with an example. We were looking at a oil service rig. This graphic you see is an example of such a rig. It pulls stands of pipes out of the well, and looking at the large drum mechanism that connected to the cables, that initial spin up of those drums was a significant source of inertia that we had to look at. And it was worthwhile looking at that calculation in detail to really understand if each spin up was a source of power that the ultracapacitor would be useful to assist with. Another example of an average you should avoid, you should specifically look at the efficiency zones of your electric motor or the devices you're utilizing in the system. Here we're just showing an example of an electric motor with its efficiency curve. And you can see in the red zone, that's a 94% efficient machine. Good efficiency, good use of the energy we have. But in the beginning on the left side, at every startup, it's going to pass through an 80% efficient zone. And if we over torque it on the right, it might experience a 60% efficiency zone. Those two zones do add up and do play a role in pushing that current higher and higher on your battery pack, and could be a good place to apply ultracapacitors to avoid these issues. One more example of an average to avoid is elevation changes. If you average a route, or here we're going to use the example of a train, and you average it as level, but it actually has some changes in elevation, those can be significant. And here I have an example just to give us some rough orders of magnitude here. Accelerating a passenger car from 0 to 60 miles an hour in 8 seconds is about the average. And that actually equates to 3.35 meters per second squared. And when we compare that to gravity, which is 9.8 meters per second squared, you can see it's actually a lot less. So even just that rough idea of accelerating a passenger car at the average in the industry is less than the acceleration of gravity. So the airport train launching from a low point actually could be a significant source of energy and a significant peak of power that we want to be aware of. That initial load of launching, let's say, an airport train from one station to the next could be a significant point that you're overcurrenting the electric system that you've implemented, where an ultracapacitor would be perfect for that application, to take that peak, apply the load to itself instead of the battery, and keep that current rating low. Another option is to data log a physical system. This would be preferred, to be able to put a pecan device, a capacitor memorator, or picoscope, or some type of device on the system to capture the data that you need. That would be preferred over a simulation. But you have to capture the right data. So one thing to look at is clearly power versus time. Understand the kilowatts needed to do the job. And you can see that across the duty cycle of the application, how that changes. And if you have that, you can also characterize an energy versus time profile. And we typically talk about that in kilowatt hours per mile for transportation vehicle type projects. But you have to understand what type of duty cycle you've now captured. Is it the 50 percentile route where this route is characteristic of 50% of the routes by that customer in that industry? Or is it a 99th percentile route where this actually covers 99% of the routes we're going to experience? So if we design for this, we'll capture all of what we really need to apply for. Understanding that is a big piece of it. So you might have to actually data log more than one route. You might need to talk in depth with your customers to really understand, well, we captured data on this route in this way, but how many more should we do? How much statistical significance do we really need? Another thing to note is where you're capturing the data. In what part of the system are you actually data logging? Because mechanical losses can be significant. Here we just show a simple calculation of the efficiency of a powertrain from the inverter through the motor, through a transmission, and a generic gearbox or differential. And it actually adds up to potentially 64% efficient. So understanding where you're actually capturing the data is important and could be very significant. For example, are you capturing the wheel torque and wheel speed from a dyno perhaps? Are you capturing the information out of the motor on the mechanical side? Or are you capturing the information out of the inverter or into the inverter? Is it the DC side or the AC side? The closer we can get to the DC side of the input to an inverter in this application, the better we'll be in characterizing what we really need to apply for an ULTRACAP system to be significant. So okay, we talked about the things we need to think about. Let's go through an example together. Here we'll talk about a load leveling system. In this example, we'll use a Freightliner Cascadia 80,000 pound GVW Class 8 vehicle. It was placed on a dyno and performed an EPA driving cycle at 70,000 pounds full weight. We took data logs at 100 milliseconds, captured engine torque and speed, vehicle speed, and wheel torque. On the right here you can see the vehicle speed in orange and the engine power in blue. And we can use the engine torque times the vehicle speed to understand the engine power, and we could use the dyno information to confirm the system efficiency. So we could see the input to the output and understand the efficiency of the whole system. So how do we analyze this data? Well, one thing you could do is you could calculate the rolling averages. So if you look across the full test, the very highest peak was 433 kilowatts. If you do a 30-second rolling average, the highest peak you achieve is 390 kilowatts, and so on and so forth until if you look across the entire test, the test averaged 75 kilowatts. Now this information will be useful in the next set of calculations, so we can use the 5-minute average and the 30-second average to really see what an ultracapacitor bank might help with. But you can also look at the energy efficiency of the whole route, and here we calculated the average was 3 to 5 miles per gallon. Using some SAE conversions, that equates to 4 to 8 kilowatt hours per mile. And also a point to note is when you're going on a dyno, when you have multiple runs, you can confirm the data acceptability. You can look at the standard deviation between multiple runs. You can do a regression test on the data against the target and show that you are correctly achieving the target profile each time, and you can really confirm the data acceptability of multiple runs and have confidence in the data you're using. Okay, so now we have the data around how much energy we need to achieve a certain route profile, and we know how much power we need for that type of profile. So now we look at the application and we say, how much range do we really need? Let's say we're doing a port delivery vehicle, so a 50-mile range would be appropriate. Maybe we have opportunity charge midday, and this is going to cover a 75 percentile application in the ports. We say, okay, now we know 4 kilowatt hours per mile times 50 miles is 200 kilowatt hours, and we can put 200 kilowatt hours on the vehicle. What does that equate to as far as our C rating? 200 kilowatt hours at 600 volts DC is 330 amp hours. And so 2C would be 660 amps. So will the peak that is drawn in this application cause an overdraw? And it turns out 433 kilowatts at 600 volts is 720 amps. Yes, that is more than the 660 amp 2C rating. And even the 30-second average also gets very close to the limit. And if you look on the right here, this is actually a typical C rating graph for a particular battery. And you can see the C rating of just using the 2C rule isn't really telling the whole story either, because that's the 2C rule at a certain temperature range and a certain SOC range. And as you go outside of those ranges, you get a little hotter, a little colder, or a little higher in SOC, that suggested C rate actually drops. So there could be additional benefits of applying an ultracapacitor system to drop the current on the battery even if you're close to 2C. And the more capacitor you can put, the more helpful it may be to keep the life of that battery up and keep the efficiency to your customer high. Okay, so now we've seen that ultracapacitors could be useful in this application. However, how much ultracapacitor capacity is actually needed? So one way to look at this is to actually go back to our rolling averages chart and assume for a moment that the battery can handle some section of the rolling average. Maybe that's the 30-second average, maybe it's the 5-minute average. And you look at that and say, okay, well, the battery will take care of that, but let's look at all the other peaks that we'll have to accommodate then. And if you look at it this way, this peak on the right is 120 kilowatts peak, 10-second duration, and roughly a triangle. So we can actually calculate the energy in that power spike, and it equates to 0.18 kilowatt hours. So now we have an idea of how much capacity could be useful to ride through one of these peaks if we put less battery on board and use more capacitors. However, another thing to look at is looking at regen current, because regen current is going to be a big piece of this efficiency improvement as well. Here on a dyno, that's not so easy to capture. We're not capturing the regen in an engine application. However, battery packs tend to not be able to capture as much regen as possible because of their ESR. You start pulling in energy, the battery voltage climbs through the ESR, and you're limited on how much you can capture. So looking at these peaks also on the regen side is a very valuable way to size your capacitor bank, because you're going to want to capture as much regen as possible. So now we know the battery size, we know the ultracapacitor size, but we want to optimize. Let's maximize battery life, let's maximize the amount of regen current we can get, let's maximize the life expectancy of the system and the efficiency of it. So you can look and say, well, if we put 0.1 kilowatt hours of ultracapacitor capacity, we can keep that peak power on the battery down to 350 kilowatts, or 1.8 C. But if we increase it, we can bring it even further down and get us down to 1.5 C. And this graph on the right really tells the story that if you can get the ultracapacitor to deal with all the peaks and the battery, even the negative peaks of regen, and the battery current becomes very, very stable, this is a really good application to go show your battery vendor and say, here's the battery current profile we expect. Please warranty it to a large number of cycles, or you can negotiate in that direction. But be aware that you have to size the DC-DC as well, so you have to optimize that part of the system as well to really understand, if I put 120 kilowatt DC-DC, it'll cost X, and I'll be able to get down to 350 kilowatts on the battery. But if we bump that up just another 30 kilowatts, we can achieve this better efficiency zone on the battery. So these are pieces that you have to be aware of and optimize to make the system the best it can be. Okay, so we've optimized the ultracapacitor, we've optimized the DC-DC, and we know how much battery we're going to put on the vehicle. But we should do some comparisons. One thing we can compare is the cost. One ultracapacitor module versus replacing a battery pack through its life. Would multiple changes of a battery pack be acceptable to the customer? What's the cost of a replacement battery pack? Chances are an ultracapacitor addition will be cheaper. Or ultracapacitor system versus having to parallel multiple battery packs. If you parallel the battery packs, you'll keep the current down. you'll get more energy for the application, but if the application doesn't need the energy, an ultracapacitor is likely a much better cost comparison. You can also look at the life expectancy. We talked about this in the beginning, but an ultracapacitor system might be rated at 1 million cycles. A battery would be an order of magnitude below that. And of course, we can look at weight. A lot of transportation applications, weight is an issue. One ultracapacitor in a DC-to-DC could be around 50% of the weight of another parallel energy storage system if we're just talking about getting enough energy, enough power capability, I should say, onto the vehicle. So now how do we integrate them into our system? What are the different methodologies we can use and architectures we can use? One application that's very common is a parallel hybrid. This type of system would focus on capturing the energy in a slowdown and reusing that energy at the next launch. So in an application like this, you might expect an engine driving the vehicle, adding an ultracapacitor bank that might be sized to 2 times the amount of energy as the kinetic energy of the vehicle you'd expect, and size the inverter and the electric motor to power the vehicle and capture as much regen energy as possible, and relaunch the vehicle using that to keep the engine load down. But be aware that you have to plan for the voltage swing of the capacitors when you size the inverter, and you have to plan for the current that you'd expect at the lowest voltage of the ultracapacitors to size the inverter appropriately in this kind of application. Another application is a load leveling system on an electric vehicle. We've talked about this, but this is to take the peaks and valleys off the battery. Remember, if you're connecting with the DC-to-DC, it needs to be sized for the power demand. And if you're connecting directly to the battery, the capacitor voltage will be dictated by the battery voltage. This is typically not done. The battery technologies that we have today tend to have a more flat voltage curve. Ultracapacitors will need to range through a significant voltage range to really discharge their energy, as we see in the calculations early on. However, there are certain battery technologies that do have a large voltage swing, and a small ultracapacitor pack directly on that battery might be useful. But here is the basic architecture of such a low leveling system. Finally, another application might be a series hybrid. Here you're trying to maximize the regen energy capture and maximize the engine efficiency or the constant power source efficiency. We think of a train. You might have an ultracapacitor take in all of that energy because it's slowing down, and the ESR of a battery would be too high, and the current would push the voltage up and limit the system, whereas an ultracapacitor, its ESR is much lower and will not limit the system as much. Think of a train slowing down and relaunching. That is very effective use of ultracapacitors if it's sized correctly. And your engine and generator would provide the average power, and there the average really works out, that the constant power source, maybe it's a fuel cell, maybe it's some other technology, maybe it's a gantry charging system, but the ultracapacitors are the ones directly connected to the vehicle, and your inverter has to be sized to deal with the larger swings that the ultracapacitor will experience compared to some more typical battery technologies. So thank you for listening. Hopefully you've learned how ultracapacitors could play a role in improving the efficiency of systems in the transportation industry in a variety of ways, be that load leveling or capturing more regen from the system. And hopefully you've experienced how to walk through that design process of understanding your system, sizing the ultracapacitors appropriately, optimizing that selection, and really doing a good cost comparison to prove that the efficiency is improved with an ultracapacitor system. So again, my name is Michael Kuhl. Please reach out and email to me if you have any questions that I can help answer, or if you need any help in this area inside the transportation industry. Thank you very much. Take care. Bye-bye.